Welcome everyone. Today we've got our Chapter 7 video, and closely related to scatter plots, we're now going to talk about linear regression. So the example we're going to be coming back to throughout this lesson is a fat versus protein scatter plot. And what we have on this scatter plot is the total grams of fat versus the grams of protein in 30 items on the Burger King menu. Okay. So using what we've seen in the previous chapter, chapter 6, we could calculate our correlation or our R value, and we'd get an R value of 0.83. So using that value in addition to the graph, we could say that there's a fairly strong linear positive association between protein grams and fat grams. Like I said, this is an example we're going to be coming back to as we start to talk about line of best fit or linear regression. So with any scatter plot that has a somewhat linear pattern, we are able to create what's called a linear model. And a linear model is just some equation of a straight line that represents most of our data quite well. So if you guys remember back to Algebra 1 and Algebra 2, we talked about y equals mx plus b form. That's exactly what we're going to see in Unit 2 with linear regression. So in a scatter plot, almost never will you see where all the points line up perfectly straight. But what we can do with a linear model is draw that straight line in so that we can summarize the general pattern with only a couple of parameters. Okay, so instead of dealing with 30 separate points, we can talk about a general slope and a general y-intercept of our scatter plot. And the linear model can help us understand how the values are associated with one another. So with our linear model, we have something referred to as residuals. So very seldom is our model going to be perfect, regardless of what quality of line that we're able to draw. So even if you are plugging in an x value into that line equation, very seldom is it going to land exactly on where that point was. Okay. So the estimate made from the model is called our predicted value, which we call y hat, or our variable name hat. And oftentimes we write this in terms of variables. So for example, if we're trying to predict somebody's weight based off of their height, well, what we would say here is that because we have that hat on top of weight in our equation, that means we are trying to predict what the weight is based off of somebody's height. Okay, so in this model, we could enter somebody's height. Let's say they're 68 inches tall, plug in 68 for height, and then once you simplify the right side of this equation, that would spit out our predicted weight of that 68-inch person. So when it comes to residuals, this refers to any error that we see when using a line of best fit equation. There's going to be a difference between what the model tells us should happen and what actually happens in reality. Okay, so the difference between the observed value, so what we actually observe, and its associated predicted value using the model, we call that our residual. So to find our residuals, we subtract our predicted value from the observed one. The best way to think about this, in my opinion, is we are in AP statistics. So the residual is equal to our actual value minus our predicted value. So a couple of key features about residuals. If we have a negative residual, that means when we take our actual minus predicted, that we get a negative number. That means that we have overestimated. So that means our predicted value is greater than our actual value. And on the flip side, if we have a positive residual, this means that we underestimated what the value was. So in this example, in this figure, you see that the estimated fat content of the BK broiler chicken sandwich is 36 grams. So that's what is on our line. That's our prediction line, that red line. While the true value is only 25 grams. So our actual minus predicted, 25 minus 36 is negative 11. That means our residual is negative 11. And again, that would just indicate that we have overestimated what the actual content is. In addition to hearing about the linear model or the line of best fit, you might also hear the phrase least squares regression line, All three of these mean the exact same thing. When we say least squares regression line though, what that refers to is that when you have a scatter plot and you draw a line of best fit in there, you're going to have some residuals that are positive and you're going to have some residuals that are negative. And on the average, they're going to cancel each other out. So if we were to add all of them up, they would cancel each other out. Okay. But with a line of best fit, we want to find the line for which the sum of the squared residuals is as small as possible. Okay, so what we're doing is finding the line that passes through the points in such a way that our residuals are as small as possible for all of our points. Okay, a lot of people coming into AP Stats in the past have thought that we find the line that passes through as many points as possible, but that is not true. What we want to do is find the line that minimizes our residuals for every point as much as we can. So going back to Algebra 1, you all are very familiar with y equals mx plus b. M was the slope and b was the y-intercept. We are going to use that same kind of format in statistics, but instead of y, we're going to replace that with y hat. Again, that just emphasizes that we are predicting. We are not saying for sure what somebody's weight is going to be, or for sure how many grams of protein there will be. So y is replaced by y hat. Then we do flip around our y-intercept and our slope terms. So b sub 0 or b naught, that's what we refer to as our y-intercept. And then b1 is now going to be our slope. And what our model tells us is that our predictions from our model are going to follow a straight line. Again, this does not mean that our actual data is a perfectly straight line. Our model that we're using to represent the data is going to be in a straight line. And if our model is good and appropriate, that means that the data will scatter relatively closely around that line. So as I said before, B1 and B0 or B naught are our slope and y-intercept. B1 is our slope. That tells us how rapidly our y changes with respect to x. And B0 or B naught, that is our y-intercept. And it tells us where the line crosses or intercepts the y-axis. Now, typically from the context of a problem or just the information given in a problem, you will be given the slope and the y-intercept. We might talk about these closer to the AP exam, but on your formula sheet for the AP exam, there are two formulas. One will tell you the slope and one will tell you the y-intercept, if for some reason they are not given to you in the stem of the problem. But for now, don't worry too much about this. Now, this is something we're going to talk quite a lot about in class, or at least we'll have some practice with it. In addition to just writing out an equation and using that equation to make predictions, we also have problems where we need to read a computer output, okay? So a couple of things that are included here. The first thing you'll notice at the top is the dependent variable, and that is what we are trying to predict based off of our x variable, okay? R squared, that will mean something to us later. If you remember the correlation value R, if we square that, that's our R squared value. That's R squared tells us something different. Then if we look here, we have our intercept, and the coefficient of our intercept is 6.83. That just means that is our y-intercept, okay? And then the coefficient in front of protein gives us our slope. So slope here would be 0.97. And this stuff on the right side doesn't mean a whole lot right now. We might talk about it later at the end of the year, but for now you can ignore that. The main part you need to realize from this table is where is the slope and where is the y-intercept. And typically it will say intercept is some number. In this case, intercept is 6.8, and then you just know that the other number is your slope. So going back to our original example where we had Burger King menu items, we see that we have a general linear pattern here, so we can actually find that line of best fit equation, and I found it right here. So instead of writing y and x, I have that our predicted fat grams is equal to 6.8 plus 0.97 times grams of protein, okay? So for example, if we were to pick the BK broiler chicken sandwich, which has 30 grams of protein, if we plug that 30 in for protein, we get 6.8 plus 0.97 times 30, and that's equal to 35.9 grams of fat. Okay, so 35.9, that would be our estimate for the grams of fat, but the actual, it turns out, is 25 grams of fat. So again, even though our model looks pretty good, it fits the model pretty well, there's going to be some residuals in many cases. So talking just a little bit more about residuals, a residual, again, that's your data value minus what your model tells you it should be, or it's our actual value minus our predicted value, or if you prefer to look at it graphically, if the blue line is our model, the black points are the actual values, then we want to take our actual minus predicted, and that red line there represents the residual. So with residuals, we actually can come up with a new type of plot called a residual plot. And a residual plot tilts our line of best fit so that the line now becomes a horizontal line. So right now, our red line, if you look at it, goes from the bottom left to the top right. Definitely a positive slope there. And what we do with the residual plot is we tilt that so that it looks like this. Look at those animations, okay? And as you can see, the points around the line are plotted exactly the same, but if we had a residual plot, then our y-axis, all that does is plot what the corresponding residual would be. So how far away from our prediction line are each of our points? So let me show you an example of what it would look like for this graph. So more formally here with our new y-axis, we have turned that red line of best fit into a horizontal line. And just like I said before, our points are plotted just as they were, but now our y-axis represents what our residuals are. So you can see at the very top towards the middle, we have a point with a very large positive residual, but we also have many on the low end as well, okay? So one thing that's really important to realize is that if a line of best fit appropriately approximates our data, we should see no pattern in our residual plot, okay? In other words, random scatter in a residual plot is a good thing, okay? So oftentimes on the AP exam, they will ask you, based on the residual plot, is our line of best fit appropriate? Well, if you don't see any distinguishable pattern within our residual plot, that would indicate that yes, it is a good fitting model. One of our last topics for today is on that R squared that I talked about in the computer output, and R squared refers to the variation accounted for. So if we think back to our Burger King example, if we had a correlation of exactly 1.0 and the model predicted the fat values perfectly, the residuals would all be 0 and we would have no variation in our scatter plot. However, we saw that it was not a perfectly straight line and our correlation value was 0.83. So it was a strong positive correlation, but it wasn't a perfect correlation. So what we can do is we can determine how much of the variation is accounted for by the model and how much is left to the residuals. So the squared correlation, if we take our R value and we square it, that gives us the percent of the data's variation that can be explained by the model, okay? And therefore, if we have that percentage, if we take 1 minus that percentage, it is the percent of the original variance that's left to our residuals, okay? So for the Burger King model, that means 69% of our variation in our data can be explained by our model, but 31% of the variability is accounted for by other factors. Now, if we have an R squared value of 0, that means that none of the variation in the data is in the model. All of it is still given to our residuals. And when interpreting a regression model, you need to tell what R squared means. So in our Burger King example, we would say 69% of the variation in total fat is accounted for by the variation in protein. Now, this is something we're going to talk about in class. I have a really good example that makes R squared much clearer. But in terms of AP exam preparation, you can say that r squared percent of the variation in our y variable is accounted for by the variation in our x variable. Just some final thoughts on r squared. So at the start of the year, I said that statistics is all about variation. And what r squared does is it measures the success of the regression model in terms of the fraction of variation of y accounted for by the regression model. Okay, so that script that we're talking about, what you need to be able to interpret r squared as is blank percent or r squared percent of the variation in our y variable can be attributed to or can be explained by the variation in our x variable. When we come to school or the next time you're in class, I will give a pizza example, and I really do think that this will help clear things up for you guys. One of the most important things about linear regression is exactly our last topic for today, and it is on interpreting slopes and y-intercepts in the context of a problem. So what we need to be able to do is if I give you a line of best fit, and I, for example, in this fat and protein example, I want you to interpret what 0.97 means and 6.8 means in the context of the problem. Well, in general, our slope, what we say is for every 1 unit increase in our x variable, we predict whatever our slope value is, increase in the y variable. And for y-intercept, we say if our x variable is 0, we predict a y variable of whatever that y-intercept is. Of course, you don't want to just say x variable, y variable. You want to plug in those actual variables, the name of them. So in our example, for slope, in this case, 0.97, we would say that for every 1 gram increase of protein, we would predict a 0.97 gram increase in fat content for each Burger King food item. Again, you really want to make sure you're using the word predict because we are not saying for sure that the fat grams will go up by 0.97. We are predicting that that will happen. Then for our y-intercept, we would say if a Burger King item has 0 grams of protein, so if our x variable is 0, then we would predict that we will have a 6.8 grams of fat in our Burger King item. So if we plug in 0 for protein, what do we get? We get 6.8 grams for fat. So go ahead, take a look at the homework assignment, maybe get started, but when we get to class, we will talk about r squared, and we'll also talk a little bit more about how to interpret slope and y-intercept.